Great to see you here again. We're continuing with number theory and cryptography. And in this video, I will talk about the different integer representations and algorithms. We're going to look into the different representations, and most of the time we are using the decimal form, the decimal representation, which is basically using base 10. It's the representation that we use in our daily numbers. Now, when we look at computers, we will see that we have different representations with a different base. And basically, it is possible to express integers relative to different bases. So we can select a different base. It doesn't have to be 10, it can be 12, it can be 2, it can be whatever base it may be. The base is an integer which is larger than 1. Once we select it, we can find the expression of any number, any integer, taking into account the new base. Typically, we know the binary representation, which is using the base 2. We also talk about a base 8 when we refer to octal representations. Now, one of the representations that is used a lot in computer science is the hexadecimal notation, which has a base equal to 16. Basically, we could use any number for the base. We can use a base number b. B has to be larger than 1. And we can, for every number or for every integer, we can define the b base representation. Let's have a look at the representation of integers that we can have. So basically, the decimal representation of the number 12,234 can be written as 1 times 10 to the power 4, which is 10,000, plus 2 times 10 to the power 3, plus 2 times 10 to the power 2, plus 3 times 10 to the power 1, plus 4 times 10 to the power 0. And basically, this is the way we represent a number in the decimal representation. So we have the coefficients of the powers of 10, which are in fact given in the number 12,234. This is the classical decimal representation. Now we can do it for any base number larger than 1, and we can have, let's say, the general expression of the representation of integers, where we have those coefficients, the 1, the 2, the 2, the 3, and the 4. We can call them the coefficients A index I, and we can create the following expression. So an integer at, let's say, relative to any base b, can be written as the sum of the products of the coefficient A index k times b to the power k, plus A index k minus 1 times b to the power k minus 1, up to plus A1 b to the power 1 plus A0. Basically, these are the coefficients A, k till A0, which are in fact the elements of the decimal representation, and b to the power k, those parameters represent the base, and the base has to be larger than 1. K is a non-negative integer, and ai are non-negative integers, and they are smaller than b. So we would go from 0 up to b minus 1. AK is different from 0, which in fact refers when we have the first number that we consider has a coefficient different from 0. Now, it's not a problem if we would have the zeros in front, but basically they don't have any meaning, and we just start with the first coefficient that is different from 0. Now, in the example we had above, we can say that the base is 10. In that case, k is equal to 4. We have a4 equal to 1, a3 equal to 2, a2 equal to 2, a1 equal to 3, and a0 equal to 4. And that's basically the decimal representation is A4, A3, A2, A1, A0. So that's the way we will represent the integers. Now this was base 10. Let's have a look at different base numbers. The binary expansion is one that is very popular because we use a lot of binary numbers in a lot of applications. We've already seen it before. And basically what we can say here is that b, in this case, is equal to 2. So it complies with the condition that it's larger than 1. And the coefficients a are smaller than b. It means the only possibility for the coefficients here are in fact 0 or 1. When we replace it in the general formula, we obtain the binary expansion. We replace b by 2, and we find that an integer can be written as a index k times 2 to the power k plus a k minus 1 times 2 to the power k minus 1 up to a0. And the different parameters a, j from ak to a0 are either 0 or 1. Now let's try to find the number 125 in a binary expansion. I already calculated it before, so now we can see what the result is. So I can say that 125 is 1 times 2 to the power 6, plus 1 times 2 to the power 5, plus 1 times 2 to the power 4, plus 1 times 2 to the power 3, plus 1 times 2 to the power 2, plus 0 times 2 plus 1. And basically we can write this number as 1, 1, 1, 1, 1, 0, and 1. And we put it between brackets, and I put the index 2 to indicate that this is a binary expansion. The 125, well, later we will see, we will also put it between brackets and put the base number 10 there, because 125 could be the result of a different expansion. The 1111101 that we have here, well, we don't know which expansion it would be. So we have to specify that we are having here the binary expansion. Now, when we make it a little bit more readable, what we are typically doing, we are grouping those ones and zeros in groups of 4. So we start from the right-hand side. So we have 1, 1, 0, 1 for the four rightmost numbers, and then we have 0, 1, 1, 1. So basically the 0 in front we don't really have to put there. We can put the 0 there, but it doesn't change anything to the number. It would just say 0 times 2 to the power 7. And since we said before that we are not writing the first number, we're writing the coefficient a, j has to be different from 0, so we can easily leave it away. It doesn't change anything to the number. Now let's have a look at the octal and the hexadecimal expansion. When we use the octal expansion, we change the base number from 2 to 8, and the coefficients have to be smaller than 8, so we have from 0 till 7. When we write the formula now, we see that the powers of 2 have been replaced by the powers of 8, which basically is the same expression, only we change the base number. And when we find a number in octal expansion, we find it under the form 57230 with the index 8. So basically the 8 is clarifying that this is a number written in the octal expansion. And we have to be sure how we have it, because if we don't put that number here, we may be confused. When we use a hexadecimal expansion, we change the base number to 16, and the coefficients a, k have to be smaller than 16. So basically they can be from 0 to 9, but after 9 we cannot put 10 there. We will put there A, B, C, D, E, and F. So F is the 16th number and represents in fact 15. When we have this as a general formula, and we can see, for example, that the hexadecimal expansion is written in the form F2ABC9 index 16 to clarify that we have the hexadecimal expansion. Let's have a look at some examples. First, we have the binary expansion 1101, 1001. Index 2 means that we have a decimal expansion, that we have a binary expansion, and we want to find the decimal expansion. So we go back to the formula. We can say it's 1 times 2 to the power 7 plus 1 times 2 to the power 6 plus 0 times 2 to the power 5 plus 1 times 2 to the power 4 plus 1 times 2 to the power 3 plus 0 times 2 to the power 2 plus 0 times 2 plus 1. So basically we have the coefficients 1 that we have in the binary number. These are replaced in this expression. So when we calculate it, we find that n finally is equal to 217. Now we can look at a number in octal expansion, which is 6051. So you see it can be confusing here that this number would be a decimal number, but the fact that we have the index 8, we know that we have an octal expansion. So what we're going to do now is we have 4 numbers. So the first one is 6 times 8 to the power 3 plus 0 times 8 to the power 2 plus 5 times 8 plus 1. So basically when we add up all the things, 8 to the power 3 is 512, 8 to the square is 64, 8 is 8, and then we have 1. And we add all those numbers, we find a total of 3,113. This is the decimal expansion of the octal number 6051. Let's look at a hexadecimal number. We have A257F, so we have 1, 2, 3, 4, 5. So we can say n is A times 16 to the power 4, plus 2 times 16 to the power 3, plus 5 times 16 to the power 2, plus 2 times 16 plus f. So basically we have here the number that we have, and there is a small error in the number. I have A252F, not A257F, like I said before. I read it wrong. So now we have n is equal to 10 times. So we replace A by the numeric value, the same like we do for F. So we find 10 times 16 to the power 4, plus 2 times 16 to the power 3, plus 5 times 16 to the square, plus 2 times 16 plus 15. And we basically find, when we do the addition, that n is equal to 664,879. So you see that the value goes up with less numbers we need to describe the decimal expansion, and the hexadecimal is very powerful because even with 5 numbers we can write a number which is in fact almost 1 million. These are the elements that we are going to use. Now what is also very important is that we want to transfer between binary, octal and hexadecimal. We will look into that later. So now when we look at the different elements, we can look at the expansion from binary to hexadecimal. Now we use them a lot, so we have a lot of examples where we have binary numbers or we have hexadecimal numbers. So when you see some MAC address numbers from your computers, you will see that they're basically hexadecimal numbers, and we can easily transform them into binary or binary into hexadecimal. Now we have those MAC addresses, and we can in fact change the binary expression into a hexadecimal number. So here we have the overview of the binary notation and the hexadecimal corresponding notation. So 000 is 0 in hexadecimal, 0, 1, 1, 1 is 7 in hexadecimal, 1, 1, 0, 0 is C, and 4 times 1 is F. Basically, that number is 15. Now, when we look at an example here, we have 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0 in decimal expression. And what we do now, we look in the table and we see where we find 1, 1, 0, 0. And 1, 1, 0, 0 is in the rightmost table, and that's in fact in hexadecimal equal to C. Then we have 1, 0, 1, 0. So we have 1, 0, where is it? 1, 0, 1, 0. This is basically A. Then we have 1, 1, 0, 0, which is C again. And then I have 0, 1, 1, 0. We have 0, 1, 1, 0, which is 6. So basically the number that we find is CAC6. And that's the hexadecimal equivalent. Now you see that we had here 4 groups of 4 numbers, zeros and ones, which can be replaced by 4 hexadecimal numbers. So it's very easy to transport. I transform these numbers, and it will be, let's say, that our binary representation, when we transform it into a hexadecimal, it's a lot shorter in hexadecimal. Now, when we look at the base conversion algorithm, we can have a base conversion and we can convert them into different formats. We can have a base conversion from a decimal number n to a base b. So the first step we do is to divide n by b to find the quotient q0 and the remainder r0. So the first number at the rightmost number is r0. So we can say that n is b times q0 plus r0. R0 is between 0, can be equal to 0 and b, and R0, like I said, is the rightmost number of the expansion. Then we go to step 2. So now we divide Q0 by B, and we find the new quotient and the next number. So Q0 is now B times Q1 plus R1, with R1 between 0 or equal to 0 and smaller than b. And we continue this process until we find the, let's say, we find the last number where q0 or q becomes equal to 0. Now we look at a base conversion example from decimal to hexadecimal. We try to find the hexadecimal expansion of 124792. In decimal expansion, we want to find the hexadecimal. So we first divide the number by 16. So we write 124,792 can be written as 7,799 times 16 plus 8. So the first number that we have is 8. Now we divide 7,799 by 16, so we can write 7,799 equal to 487 times 16 plus 7. So the following number is 7. Then we have 487, so we divide it by 16, so we can write this as 30 times 16 plus 7. We have 7 again. Then we have 30. We can write as 1 times 16 plus 14, and 14 represents the letter E. And then we have 0 basically, so the result is in fact given by E778. So basically all these numbers are in fact the representation of that decimal number in a hexadecimal base. Now let's have a look for another conversion. decimal to octal, so we do the same thing. We look at the number 33,702. So we divide 37,702 by 8, or we can write 32,702 equal to 4,212 times 8 plus 6, so the rightmost number is 6. Then we can write 4,212 equal to 526 times 8 plus 4, so the second number is 4. Then we have 526 is equal to 65 times 8 plus 6, which gives us 6 again. Then we have 65 is 8 times 8 plus 1, which is 1. And 8 is 1 times 8 plus 0. So basically we have 0 here. So the result of 33,702 in decimal expansion is 01646 in octal expansion. Let's look at the pseudocode of the conversion algorithm. We can say that the procedure is a base B expansion of an integer. We say q is equal to n to start with, k is equal to 0, so these are the initial parameters, while q is not equal to 0. When we continue doing this loop as long as q is not equal to 0, we say that aq is q modulus b. So here we only find the remainder. Then we say q is q division b. So now we find the module, the remainder, and the quotient, and we add one number to the set. So we put one number, we add k plus 1, and we continue the loop. We continued until we find that q is equal to 0, and we find a set of parameters ak minus 1, a1, a0, and we can say that the b base expression of the decimal number n is ak minus 1 up to a1, a0. So basically the output of this algorithm would be a binary code. When we have b equal to 2, it would be an octal code if we say b is equal to 8, and it would be an hexadecimal code if b would be equal to 16. So basically that's the way how we can use the algorithm to calculate this. Now we can also look into the conversion between different bases. We have a binary number here, 1 0 0 1 1 1 1 1 0 1 1 0 1 0 1 1 in binary base, and we want to translate it, for example, in binary or octal. Now in octal, what we do is we group the numbers from right to left, and we group them 3 per 3. So we group them as a set of 3. So we find here that we have 0, 1, 1, which are the 3 rightmost numbers. Then we have 1, 0, 1. Then we have 1, 0, 1. We have 1, 1, 1, 0, 0, 1. And 0, 0, 1, the two zeros were not in the original number because basically they don't have any real value, but we put them there because then we also have 3 numbers. And now we look into the table and we say we have 0, 0, 1, which gives us 1. So the binary of 0, 0, 1 is 1, 0, 1 is 1, 1, 1, 1 is 7, 1, 0, 1 is 5, 1, 0, 1 is 5, and 0, 1, 1 is 3. So basically the number that we had in binary code, the 1, 0, 0, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, can be written in octal code as 1, 1, 7, 5, 5, 3. We can now do the same thing for the hexadecimal number, but now we group the numbers, the binary sets by 4. So we have 1, 0, 0, 1, we have 1, 1, 1, 1, 0, 1, 1, 0, 1011. And now we look in the table, in the binary, and we find the equivalent number in hexadecimal. So we have 1011, 1011, which is 11, is in fact B. 0110, 0110 is 6. Then we have 1111. This is in fact 15. This gives us the hexadecimal number F. And 1001 is 9, so we have 9 here. So the same number in hexadecimal notation is 9F6B. And those are the way we can use those conversions, and you can use this table. Of course, you can write a program also, or some algorithm to transform or to change the base of the number and find the number in the new base number. So this was what I wanted to do in this video. We looked at the different expansions of integers, and now we will be looking at integer operations and algorithms that can be used to deal these integer operations. You're doing a great job. I hope you like it, and I'm looking forward to seeing you in the next video. Thank you, and bye-bye.